Hi, everyone. Today we're on Unit 10, Lesson 3, and we're going to be discussing more limits. In yesterday's lesson, we started evaluating limits by using direct substitution, meaning we're just plugging in our x value. Okay. When a function is continuous, this method is always going to give us our answer. So similar to like reading our answers off the table, it's just going to mean our function value matches our limit. Today, we're going to be discussing some situations that may give us problems when we try to evaluate them. Okay, those are going to happen when our functions are not what we call continuous, or when we have places where our function may be undefined or some other issue going on with the problem. So let's begin by discussing some functions that may give us issues. And those functions are going to be our rational functions. Right? When we have some f of x over a g of x. Those functions are going to be radical functions, because what do we know about a radical function? We can't have a negative under the radical sign. And those functions are going to be piecewise functions. And we're going to have a whole separate day on piecewise functions. So today, we're going to talk about what to do when you're dealing with rational functions or radical functions. So I'm just going to jump to an example first, and then we'll go back up and talk about what to do for the problem. So if we take this example, the limit as x approaches 3 of x squared minus x minus 6 over x squared minus 9. If I plug in 3 to start with, I'm going to wind up getting 0 over 0, which means when I plug in my c value into this function, it's undefined. I won't get an answer. But that does not necessarily mean there's no limit, because remember, in the first day of this unit, we talked about how we still can get a limit even though it's undefined. Okay? So instead of going to our calculator, we're going to talk about how we can deal with this algebraically. Well, since this is a rational function, we can factor this function simplify, and try again. Three plus 2, 3 plus 3, 5 over 6. So my actual answer is 5 over 6. Remember, what does this mean? Right? A limit. I don't care what I get when I plug in 3. I care what I get when I plug in a number a little bit bigger or smaller than 3. And I want to know what's happening on the graph of that function. And when we simplify and try again, we get what's going on in the function. Okay, so when we're dealing with a rational function, we're going to plug in c. If the denominator equals 0, we're going to factor, simplify, and try again. And it's that easy. Okay. I told you, things are going to get a lot easier from here on in. The limit as x approaches 2 of x squared minus 4 over x minus 2. Plug in 2. And I get 4 minus 4, 0 over 0. Again, we're going to factor, right? This is undefined. So we're going to factor. And reevaluate the limit in simplified form. So our answer for this problem would be 4. Okay. What do you think is happening on the graphs of these two functions? Okay. When we have a rational function and we don't get an answer where it's undefined, we can either have a hole or an asymptote. So these basically is another way to identify the holes or the missing points in our function. The limit as x approaches -2 of x minus 2 over x squared minus 4. I'm going to plug in -2. This time I get -4 over 0. This is 1 over x plus 2. 1 over -2 plus 2. Again, I wind up getting 1 over 0, so this is undefined. I'm sorry. When I first evaluate it, it's undefined. And now since I don't get an answer the second time, this means my limit does not exist. And if you recall from the other day, we had these situations. Okay. And in this type of situation, we probably have some asymptotic behavior going on. In example 4, the limit as x approaches 3 of the x cubed minus 27 over x squared minus 9. When I first plug in, I get 0 over 0, which means my function value is undefined. So I get to factor and try again. X minus 3, x squared plus 3x plus 9, x minus 3 times x plus 3, cancel. So we're really evaluating three squared plus 3 times 3 plus 9 over 3 plus 3. So I have 9 plus 9 plus 9, 27 over 6. And that's going to be 3 goes into 27, 9 times, 9 halves. Okay. So just remember, when you're evaluating a limit, if you don't get an answer the first time, you get to factor and try again. Now we can see from the examples above that anytime we're dealing with these rational functions, we're going to be dealing with x values that may be undefined. And just to re-mention from our study of rational functions, we recall that when the x values where the function is undefined can either be described as a whole or an asymptote. There are many times when you're asked to not only evaluate a limit at a specific value, but also to describe what type of discontinuity is. So if you're using limits to describe what we call a point of discontinuity, a hole is when the limit exists, and an asymptote occurs when the limit does not exist. And I hope that makes sense from some of the stuff we discussed. Next year, you may get more specific and use words like removable and non-removable. I'm going to try to introduce these words this year so that you're more familiar when you hear them again next year. But our main goal is just going to be identifying and answering the question. If I get a limit, it's a whole. If I don't get a limit, then I have an asymptote. So in our next example here, we want to first determine where the function is undefined, and then use limits to determine if it's a whole or an asymptote. Now, I know you can do this from what you know or remember from rational functions, but now because we're studying it with calculus, we want to be able to do it using limits to support our answer. So first, to find where the function is undefined, we set the denominator equal to 0. So the two x values that make this function undefined are at x equals -3 and x equals 1. So now instead of using algebra, we're going to talk about to support, to identify if a whole or an asymptote, we're going to evaluate each limit. So the limit as x approaches -3 of our function the limit as x approaches 1 of our function. Now, the good thing here, we already know when I plug in -3, I'm going to get a 0 in the denominator. When I plug in 1, I'm going to get a 0 in the denominator. So I'm going to reevaluate. I'm going to factor and simplify x plus 3, x minus 2, x plus 3, x minus 1. So I know I'm reevaluating each limit in my simplified form. -3 minus 2, -3 minus 1. -3 minus 2, -5 over -4. Since I get an answer, the point of discontinuity can be described as a hole at x equals -3. What is the actual physical point of the missing point? It's -3 5/4. But we just are being asked, we just want to answer the question we're being asked. Because if I was just being asked to evaluate, that would be my answer. But because I'm being asked to go a step further, I'm just going to kind of expand. And here, because I get a 0 the second time, the limit does not exist, which means I have an asymptote at x equals 1. Okay. So sometimes your questions will be nice and straightforward and just evaluate your limit. And sometimes your questions will be a little bit more involved. Okay, so you just have to be able to recognize what's going on when you answer a question. Now with our radical functions, when we're dealing with our radical functions, always going to start, okay, we're always going to start the same place, right? We're going to plug in C. So when I plug in C, 0 plus 1 minus 1 over 0, I get 0 over 0. But you have to remember, getting 0 over 0 does not necessarily mean you don't have an answer. So in order to deal with this, okay, what way do we have to rewrite a radical expression? We're going to rationalize and try again. So I'm going to go rewrite my function. And we're going to kind of think back to the beginning of the year when we rationalized functions. Our radical sign is in the numerator. So we want to multiply the top and the bottom by the conjugate. X plus 1 plus 1. X plus 1 plus 1. And remember your rules when you're foiling conjugates. I do first times first. I'm just going to have x plus 1. The outsides and the insides are going to cancel out. Last times last is minus 1. And to refresh your memory, in the beginning of the year, we'd never distributed, just leave that other part of the fraction alone. So I'm going to reevaluate, right? We're going to first simplify. And I'm going to reevaluate this limit. We're going to rationalize, simplify, and try again. Now when I plug into this function, 1 over the square root of 0 plus 1 plus 1. Well, what is the square root of 1? It's just 1. So we get 1 over 2. Okay, so the most important thing to remember when you're dealing with limits, you get a second chance. So if you don't get an answer the first time around, do whatever you have to do to rewrite the function and try again. The limit as x approaches 1 of x minus 1. So I have 1 minus 1. Zero over, well, the square root of 9 is 3. 3 minus 3 is 0. I need to rationalize. And at least this time I gave myself enough room to work. So to rationalize this function, we're going to multiply the top and the bottom by the conjugate. Now we're rationalizing the denominator. Right? So we're going to leave the numerator alone. Just leave it as its factors. And go back over here. So I have 4x plus, so I'm going to have 4x plus 5. Outside and inside cancel out. 4x plus 5 minus 9. Well, that's going to be 4x minus 4, which is going to be 4 times x minus 1. You see how much algebra we're using when we do this stuff? Now I'm really reevaluating this limit in this function now. It's an equivalent function. Four times 1 plus 5 plus 3. I don't know why I can't write today. So the square root of 9 is 3. 3 plus 3 is 6 over 4, which is equal to 3/2. All right. So hopefully you guys see the different situations that can arise. Okay. This is probably, if I had to say, the most important lesson, understanding what to do when you don't get an answer the first time around. Okay. And notice our shift from dealing with the table and now focusing on algebraic methods to deal with our situations. Okay. Make sure you practice that homework tonight. It's extremely important. Thank you, everybody, and see you again tomorrow.